Alright, hello everyone. Today we're going to be talking about hydrogen NMR or proton NMR. So the first thing I want you guys to know is chemical shifts. So this is right here, this is the chart for all the chemical shifts. So hydrogens are going to have different chemical shifts depending on their neighbors, depending on what they're surrounded by. So for example, whenever they have something that is really electronegative next to the hydrogen, we're going to have a high chemical shift. And whenever we're going to have something that is not very electronegative next to the hydrogen, like carbons, we're going to have a lower chemical shift. So this right here, this yellow chart, I'm going to explain it soon. I just want to make sure that you guys have it. If you want to take a screenshot, it's going to be very helpful very soon. So I want to introduce some terminology. So whenever we're talking about HNMR, there are a few words that I want to make sure you guys know. The first one is a chemical shift, and your chemical shift is going to be just bending like this way or this way right here. That's what your chemical shift is going to be. Right here, I wrote them also on top right here. On this side, you're going to have a low frequency or low chemical shift. Right here, we're going to have high frequency or chemical shift. Actually, I'm just going to change the word frequency to chemical shift. So always anything on the right is going to be your low chemical shift. Anything on the left is going to be your high chemical shift. What does it mean by chemical shift? It means what's surrounding it. So whenever I have something that is electronegative around it, it's going to be considered to be high chemical shift whenever there's something electronegative around it. So for example, look right here. I have an oxygen next to the hydrogen. Right here, I have an oxygen next to the hydrogen. So those are my high chemical shifts. What do we know about electronegative atoms? Electronegative atoms like electrons, and they're gonna steal electrons from the hydrogen. They like the electrons to be surrounding them instead of the hydrogen. So when those electronegative atoms are stealing electrons from the hydrogen is gonna become de-shielded. And that's the other word that I want you guys to know. So it can be high chemical shift is the exact same thing as de-shielded. So my hydrogen is becoming de-shielded due to the electronegative atoms that are surrounding it, or what we call also high chemical shift. Those are all the same terms that mean the same thing. And the last thing that I want you guys to know about this one, about the chemical shifts, it's downfield. Downfield is the exact same thing as high chemical shift. And upfield is the exact same thing as low chemical shift. So a quick recap about all of these. On the right side, right here, I have shielded because I don't have any electronegative atoms surrounding my hydrogens, right? So no electronegative atoms are going to steal the electrons. The electrons are still surrounding the hydrogen, so the hydrogen is shielded. It's good. And it's going to be low chemical shift, again, no electronegative atoms surrounding it. And the last word, it's upfield. Just remember, low chemical shift goes with upfield. On the left side right here, I have high chemical shift, which means I have electronegative atoms surrounding my hydrogens. Again, HNMR is all about hydrogens or protons. So if I have electronegative atoms surrounding my hydrogens, then it's going to steal the electrons from the hydrogen, and that's going to make it de-shielded. It's not shielded with its electrons anymore. My hydrogen is no longer shielded. And the last word is downfield on the left side. Alright, a little more terminology. The word integration right here. Integration tells you how many hydrogens does each signal represent. What's a signal? Signals are just these. That's a signal, that's another signal, that's another signal, signal here, and signal here. So everything that I pointed out with arrows are my signals. And one more word. So this signal right here, this one, has only one peak. Right? This one right here has 3 peaks. So sometimes they use the word signals and peaks interchangeably. I just want you guys to know that each signal is one of those. Just like that's my signals. And those little beaks inside of my signals, that's what's called peaks. So this is one peak right here, that's another peak, that's a third peak. Alright? So what are the type of signals in this? right here. Whenever I have a single beak, I call this a singlet. What about if I have three, like this one? It's one signal that has 3 beaks in it. I call that a triplet. This one right here, this signal has only 1 beak, so it's going to be called a singlet again. This one has 2, so it's going to be called a doublet. And this one is just 1, so it's again a singlet. So I know on the bottom, chemical shift. Everything on this side is going to be low frequency or low chemical shift. On this side, it's going to be high chemical shift. And this is low chemical shift, right? Always right is low, left is high chemical shift. The second word that you need to know is integration. Integration tells me how many hydrogen each signal represent. For example, this one right here tells me it's the number. It can be 3, it can be 2, it can be 1, just depending on how many hydrogen it represents. So the number of hydrogens is always represented or said under the signal. And the last thing is how many beaks are inside of my signal. Right, let's do some examples. Let's see how this is gonna work. So before we do the first example, the last thing you guys need to know is chemical equivalence. What's chemical equivalence? It's just like what hydrogens are equivalent to each other. Let's look at this example right here. In this example, I have this molecule, and the first thing I need to know, I need to see how many hydrogens there are. I have 1, 2, 3, 4, 5, 6 hydrogens, right? HNMR is all about hydrogens. So I have 6 hydrogens right here, and what I'm trying to do, I'm trying to see which hydrogens are equivalent. How do I decide which hydrogens are equivalent? It all depends on what the neighbors are. If every single hydrogen is equally distant from the other atoms in the molecule, then it's equivalent. Let's do an example so everything makes a lot more sense. So let's look at this one. This hydrogen, and this hydrogen. Those 3 hydrogens are all connected to this carbon, which is connected to this oxygen, which is connected to this carbon right here. So those 3 hydrogens are the same distance from this carbon, the same distance from this oxygen, the same distance from this carbon. Same thing for this carbon. So these 3 hydrogens are equivalent. Let's see why this hydrogen right here, hydrogen 3, is not equivalent to one of those hydrogens. Why is it not equivalent to hydrogen 4? Because hydrogen 3 right here is attached to this carbon, which is immediately attached to an oxygen, right? But this hydrogen number 4 is attached to a carbon, which is attached to another carbon. So hydrogen number 3 is attached to a carbon that's attached to an oxygen. So it's different than that hydrogen number 4 that's attached to a carbon that's attached to another carbon. So those are not equivalent because they have different relationships with the atoms surrounding them. There is right here, this carbon right here. Let's compare this one carbon to these 2 hydrogens. This carbon is only 1 carbon away from this hydrogen. But this carbon, compared to this hydrogen, it has an oxygen in between, then it has another carbon, then it has a hydrogen. So these two hydrogens are completely different. So what are my equivalent hydrogens? Again, I have these 3 to be equivalent, and I have these 3 to be equivalent. So quick tip that everyone gets to know: most CH3s are usually equivalent. That CH3, the 3 hydrogens on a CH3 are most of the times equivalent. Not always, but most of the times. So if I'm gonna just redraw this, I have this, I have an oxygen, then I have this that says CH3. So those 3 hydrogens are equivalent, and those 3 hydrogens are equivalent. So the number of signals, look, if you guys look at this chart right here, the number of signals, in this case I have two signals, right? That tells me how many hydrogen environments are there. So when I counted, I was able to tell that I have this right here, which is the first equivalent hydrogens. So these 3 hydrogens are represented by one of those signals. And this right here, these 3 hydrogens are represented by another signal. Which is which, we're going to talk about soon. I just want to make sure that you guys know are each one of those, we call it a hydrogen environment because these three hydrogens are equivalent, so they're in the same environment compared to the molecule. Exact same for these three. And each hydrogen environment is always made up of equivalent hydrogens. And those equivalent hydrogens are going to share the exact same signal. So in this case, I have two hydrogen environments, which tells me that I have two signals. Alright? If you guys remember the word integration, it tells me how many hydrogens are represented by a signal. In this case, I have three equivalent hydrogens and three equivalent hydrogens, so each signal is going to be three hydrogens, right? That's why I have three hydrogens here and three hydrogens here. And the last thing that I want you guys to know is the chemical shift. Why is one of them 2 and the other one is 4? So again, we said whenever I have an electronegative atom near my hydrogens, it's going to be a higher chemical shift. So let's compare them both. The pink ones right here, these three, have a carbon next to them, which is not very electronegative, but right next to it, we have an oxygen, right? So they have a carbon, then an oxygen. So they're right next to an oxygen. They're on a carbon that's right next to an oxygen. The other ones, right here, the other three, are on a carbon that's right next to another carbon. Then they have oxygens next to them. So the green ones, are 2 carbons away from an oxygen, while the pink ones are only 1 carbon away from an oxygen. Oxygen is very electronegative. The ones that are closer to an oxygen are going to have a higher chemical shift. So this one right here is going to be the pink ones, and this one right here is going to be the green ones. Alright, let's do one more example to make sure you guys got it. In this case, again, there are steps that I want you guys to know. First, I'm going to count how many hydrogens I have. I'm going to see which ones are equivalent. Then I'm going to see which signal represents which hydrogens. So in this case, I have these 3 hydrogens right here. And I have those right here. Again, the yellow ones, the CH3, the CH3, and the CH3, all the yellow ones are equivalent. Why? Because they're 1 carbon away from this carbon, every single one of them. They're 2 carbon away from this carbon, so they're all equivalent. And the exact same thing goes to the rest of the molecule. But these ones right here are different. These CH3 are right next to an oxygen. So those are different than the yellow ones, because the yellow ones are really far from an oxygen, right? And they're all equally far from each atom. But the green ones are all right next to a carbon that's right next to an oxygen. So those 3 ones right here, the hydrogens are equivalent, and the yellow ones, all of them are equivalent. So if I tell you these 2 signals, or how many signals I should have, you should immediately say I have 2 signals. Why? Because I have 2 hydrogen environments only. The first one is the green, so 3 hydrogens, and the other one is those 9 hydrogens from each CH3. I have 3, so I have a total of 9 hydrogens from the yellow ones. So, which one's going to have a higher chemical shift? Again, higher chemical shift is closer to an electronegative atom. Which is closer to an electronegative atom? I have the green one a lot closer to an electronegative atom. It's right next to the oxygen, right? So this one's going to have the higher chemical shift next to the 4. Again, remember, this is high chemical shift right here, and I have low chemical shift right here. And the yellow ones are really far from the oxygens. They're mostly surrounded by carbons. I have like 1 carbon here, 1 carbon here, carbon, carbon, mostly carbons, right? So it's going to have the lower chemical shift. Why is it so high? Because it represents a lot more hydrogens. This one represents 9 hydrogens, so its integration is 9. This one's integration is 3 hydrogens. Right, and this is a little shortcut that can help you. Again, this is for chemical shift. Again, I have my low chemical shift here, my high chemical shift here. And this is called upfield. This is called downfield. So whenever I have a hydrogen right here, that's right next to a carbon, nothing electronegative, it's going to be low chemical shift. That's why it's on the low side. Right here, whenever I have an alkyne, a hydrogen that's on an alkyne, it's also low. Then right here I have a hydrogen that's connected to a carbon, but there's an oxygen nearby. It's not right next to it, but it's nearby. and that's going to be right here. It's also low chemical shift considered to be. And this one right here, the yellow one, this hydrogen is on a carbon that's right next to a Y. A Y is just an electronegative atom. Whenever I have an electronegative atom, I'm going to have a higher chemical shift, and that's why it's going to be a higher chemical shift compared to the other ones. So it's going to be 3 to 4. Something that usually has a really high chemical shift right here, the next one, is whenever I have a hydrogen that's on an alkene. Whenever I have a hydrogen right on a double bond, it has a really high chemical shift. And it's going to be between 5 and 6 ppm. ppm is just the unit for chemical shift. Then if I have a benzene ring, it's going to be somewhere between like 6.5 and an 8. So all those hydrogens are going to be between something between like 6.5 and 8. Those are going to have really high chemical shift as well. And then the highest chemical shifts that are not very common, but we see them sometimes, are this one right here, which is an aldehyde, and this one right here, which is carboxylic acid. The hydrogen of an aldehyde is right on a carbon that's double bonded to an oxygen. That's why it's really, really high chemical shift. And this one right here, the carboxylic acid, if you look at it, it's an OH. It's a hydrogen that's right next to an oxygen, so it's going to have really, really high chemical shift. So it's a hydrogen attached to an oxygen, and it's also attached to a carbon that's double bonded to an oxygen, so it's going to be really, really high chemical shift. Alright, so quick recap. What we talked about is chemical shifts first. The first thing we talked about is chemical shift. I have high chemical shift, I have low chemical shift. High chemical shift means I have an electronegative atoms nearby. Second thing we talked about is integration. Each signal has an integration, which means it's going to tell me how many hydrogens each signal represents. An example, this one right here, this one has an integration of 3. This signal has an integration of 3, so it represents 3 hydrogens. This one also represents 3 hydrogens. So just how many hydrogens are represented by a signal. That's what integration is. Next, the word just signal just means those in general. Every signal is just called a signal. And those signals can have little signals inside of them, so we call those peaks. So in this case, this signal again is called a singlet. If I have 2 beaks in it, it's called a doublet. If I have 3 beaks in the signal, it's called a triplet. And last, we just did some examples right here. Just know the chemical equivalence, what hydrogens are chemically equivalent, because the hydrogens that are chemically equivalent are always going to share the same peak, the same signal. Notice again that those 3 hydrogens are chemically equivalent, right? They're distant from everything equally, from everything in the molecule. There's the same distance to this oxygen, there's the same distance to this oxygen, because they're all on the same exact carbon. So those are equivalent, which means they're going to be represented by the same signal. And if you look at it here, this signal right here represents these 3 hydrogens, and they're all represented by that one signal. Same thing right here, these 3 hydrogens are represented by the green signal. So chemical equivalence, all my chemically equivalent hydrogens are going to be represented by the same signal. But these hydrogens are not equivalent, and that's why we have 2 different signals for them. And this is the last example we did that covers the exact same thing. Hope this was helpful.